Swayam Prabha. Digital India. Educated India.
So hi, welcome back again. So let us start today's class by looking at some nice pictures, okay? And we won't discuss them, just look at them and then we'll see what we're talking about, okay? So let's go to this one and see if we can, okay. Now this is a small slide I sort of put together. It's the kind of flows, possible. So, and these are also some sort of wide range of stuff that I'm interested in, and I like to look at work. I do some work myself also, right? So I think this is a broad categorization of flows. Why that is necessary in fluid mechanics is something that you should acquaint yourself with. Why do we have to sort of do this? So broadly, you would have say subsonic flows, which is Mach number less than flows, Mach number less than 1, and this is where we're going to tackle turbulent flows that we are talking about, and you could have boundary layers as well in turbulent flows. I do not know if we will be able to cover all of that in this in this course. We'll see. Okay, depends on the amount of time we have. Then, of course, before you go to high speed or supersonic flows, there is this where you have like shock waves, etc. There is this middle path somewhere, transition phase, where you go between subsonic to high speed, and that is the transonic flows, which is Mach number ranges between 0.85 to 1 maybe, right? And I've done some work on this as well. And then, of course, this is something typically which I do for a living almost, which is high speed flows, high alpha flows, and typically for airplane wings, it could be for an angle of attack, which is, little around more than, 10 degrees, 12 degrees. So here also you encounter turbulence because these are very high Reynolds number flows. The boundary layers are very thin, they separate, and the moment you have flow separation, you're talking about turbulence. Okay, we also have turbulence in transonic flows, and subsonic flows. Of course, we have turbulence flows. So this is to kind of drive home the point that we are dealing with a topic which you pretty much have to deal with no matter what sort of flows you're dealing with. So whatever you want to study, turbulence is not something that you're not going to encounter. So how you want to deal with it, whether you want to learn it, how much you want to learn it is of course up to you. But this is an interesting topic which would pertain to anybody who's trying to study fluid mechanics in general. Okay, so so for example, these are some pictures that I have here. Okay, so let's just say these these two pictures of oceans, basically from a personal collection. These are two oceans, right? One in Hawaii, one in Goa, right? And do you see the difference between the two? Okay, and if you see the picture right here for the Hawaii ocean out here, okay, you see the different colors. It's the same ocean, the different blues, right? You can see waves. And what's up with this white? You must have seen this. And also when you have boats, when you have ships, you see a lot of white, and it's called white water actually. Okay. This, so like I said, we will not discuss this, but I'd like you to sort of notice that we do have this white thing here, right? This Hawaii picture, of course, I think is on a very clear, bright day. Sky is very clear, and you see the ocean looks like that, right? And this is in Goa, and clearly you can see the sky. It is very overcast and ready to rain, and the water is nowhere blue. Interesting, right? And there's a lot of white going on here. You know, what is interesting is there's a lot of white going on here, and what I would like you to do at this point of time is, it might be a small thing, but look at, for example, a tank of water. You know, anywhere, a small tank of water, a glass of water for that matter. The surface of that water, try to compare the surface of that water with the surface of the ocean right here, right? Yeah, it's very large, but what I'm talking about is really the surface of the ocean and the surface of, say, a water which you're carrying in a small tank, right, or in a glass, right? Sometimes we store water at homes. So how does that surface look like, right? And why is it that these look so different, right? Why do we have such white stuff going on here in this picture from Goa, right? There is white stuff here as well in the picture from Hawaii, right? This is on a very overcast, almost rainy day, whereas this one is on a very clear day, right? But then we still have that white thing going on here. You know, it'll be interesting to figure out why, right? Interesting to figure out why we have this. You know, you will also see this kind of white stuff when, you know, there are ships and you know, even little boats. And I'd like you to also think of a possibility where you're in a small boat. You know, or maybe you've already faced this. You know, you're in a small boat, and yeah, you're in a small boat and a big ship passes by, or a big, like a motorboat passes by. You're quite far away actually, right? What do you think will happen? You know, what could you face, and why would you face that? Okay, those are questions you need to answer. Okay, think about it. Okay, so another thing is, if you look at, this is the smoke from a matchstick. What you could do at home is switch off the lights, you know, light a candle. Yeah, well, just switch off the lights. It will be very dark, and study the smoke from an incense stick, agarbatti, right? Take an incense stick and just sort of, you have to throw light on it, otherwise you can't see. So maybe, you know, a small flashlight or something. So you can do that and just look at the smoke, study the smoke. So this is, as you can see, this is a matchstick here, right? So you could, and this is the smoke which is generated, right? So do you see, why isn't the smoke like, you know, a nice plain piece of cloth or paper, right? It seems to be winding up. You look at these, right? Look at this structure here, how the smoke sort of winding up. Look at these here, look at this, right? If I were to sort of, you know, almost like draw a section like this, almost draw a section right here, you know, if I were to draw a section, okay, I can't do that there, something like this here, okay, what does this look like, right? Interesting. So again, if you look at that, and this is an aircraft, right? This is an aircraft in flight, and maybe next time you fly, you know, if you try to look out of the window, maybe you can spot some things like that, okay? And here too, what I see is things like these, right? I see things like these here, okay? Interesting. So like I said, we will not discuss this, but, you know, nice to see sort of an airplane in flight, right? And you have a smoke from a matchstick, you know, and you could just take a like I said, incense stick and look at that. Do one more thing, you know, take a candle, place it place it near the incense stick, like when you have an agarbatti, right? And see what happens to the smoke. How is it different? It's very interesting. Just switch off the lights in your home, and just for a 15 minutes, and do this exercise. You'll find it very, very interesting, and you'll see things right in front of your eyes, you know, right around you. Okay. Wow, this is a picture you probably have seen, the one on the left hand side, right? So this is something you probably have seen earlier on, okay? And so this is an airplane again, right? A dye has been injected into the air, and what you see around its edges again, I might be able to sort of point this out. Do you see this? The structure right there. You see the structure right there, okay? And this, the one on the right hand side here, this one, this is the flight, this is the plane, and this is the aircraft, and this is what it is leaving behind it. This is the structure which is leaving behind it. Again, I think I can spot these things out here, if you see. And what is interesting, there's a small little eye in both cases. Do you see that? There's a small little eye here, right? And then something, really, this is also smoke which is being done here, right? Interesting. Okay, so this is from an air show. Actually, these pictures are from an air show in 2009, Aero India at Bangalore. And these are things you watch on TV all the time, and if you see, the question to ask, of course, is that when you have things like this, and these are injecting smoke into the air, right? It's all very nice, but why? So this is the smoke structure. If you see here, why isn't like a nice plain line pipes? Why? It's all nice and wiggly types, right? So why isn't it like a nice solid pipe? Why not? But what is going on here with the smoke? How is this behaving? Okay, and if you see here also, if you see in this picture also, the smoke being left behind, you see the smoke being left behind. One more thing to notice would be the smoke when it is right next to the at the time of the smoke being ejected out, it's a little thicker, the white is kind of distinct, and then it kind of fades out, right? So what is going on here, right? What is this thing that we have even different densities apparently when I look at this, right? Okay, this is this is actually a photo of a tornado developing, right? It's actually a tornado developing. So this is how the clouds, this is the ground actually. There's a ground, as you can see. This is the sky. It looks menacing actually, and then you see how so these are people, a group of people actually, who study, cyclones, right? And they do this, and so they have some quite some magnificent pictures of the wonders of nature, basically, right? And so you see, this is basically development of that, development of this fluid flow, I guess, every instant of time, and see how dark it gets, man. You see this, right? And finally, you see something like this. You have this snout right here, and you see this is the swirling mass of fluid, right? So that is essentially a cyclone. People call it different names: cyclone, hurricane, tornadoes. So we've talked about, we've seen a lot of pictures actually of turbulent flows, and the one that you saw just now, probably looks like one. But let's discuss that a little bit. Okay. So this is the typical contrail of an aircraft, right? The trail it leaves behind when an aircraft moves, right? So this is the exhaust from an airplane, right? And these are the tip vortices, as you probably know. And you saw the pictures, right? The question is that the picture, when you see that, right, at the first look at it, it does look like a turbulent flow. But turbulent flow has certain characteristics, right? So just because a flow kind of looks like a turbulent flow, is it actually turbulent? Does it follow all the characteristics that are required to be a turbulent flow?
I think we'll look at that a little bit in detail. Okay, and aircraft contrails are a good example of that. Okay, so not everything is turbulent, although they look like it, in the pictures. Okay, so here too I'm going to cite a reference for you, so you can take a look at it. So this is it. So for example, transport and effective diffusion of aircraft emissions. This is the reference. So Gers, Turbeck, and Konopka, Journal of Geophysical Research, 1998. Okay, so as I'm talking about, so the exhaust from the airplane, as you can see, right? These are the tip vortices, right? So this exhaust from the airplane is isolated and concentrated primarily in the two wingtip vortices, right? That's the wingtip vortices, and this is the primary wake. Okay. So primarily, most of the exhaust is actually concentrated in the tip vortices, and very, very strong tip vortices, and this is the primary wake. Okay, and due to the strong induced velocities of these two trailing vortices, right, of the primary wake, 10 to 30% of the mass of the exhaust gases is entrained into the surroundings, right? So because of this, it's entrained into the surroundings, and that forms the secondary wake. Okay. Okay, so if you use your right and thumb rule, you will see how the velocity vector, in which direction the velocity vectors will point. Okay. So like I said, the 10 to 50, it's only 10 to 30% of the mass of the exhaust gases is concentrated in is kind of distributed in the secondary wake. Okay. So this is what we're talking about here. Okay. Now this flow that you look at, is this turbulent or what? Okay. And it's like long. It's kind of traveling. Okay. These gases, which are exhaust, right, into the atmosphere, and then they are traveling. So there is dispersion of this exhaust plume, and there are three regimes to that. Okay, number one being the jet regime. Okay, so so the moment the exhaust gases are generated, right, or are jets, or are basically exhaust from the airplane into the atmosphere, right? So what they do is there is a vortex sheet that rolls up into the counter-rotating tip vortices. Okay. Now this is the jet regime. So that's the jet regime, right? The next is the vortex regime, right? Where these tip vortices travel downstream. Yeah. Downstream, and the exhaust also sinks below the flight level, right? As it is stored in the primary wake. Okay. Some of the exhaust is also retrained in the secondary wake. And finally is the dissipation regime. Okay. The dissipation regime. So this is essentially organized vertical motion, right, that breaks up, okay, into turbulence, and its energy dissipates. Okay, so initially, actually, when the exhaust gases are let out, okay, they expand freely first, right? They expand freely by evolving the tip vortices. They expand freely, but then the tip vortices, because of the induced velocities, they draw them in, and they concentrate that, and they literally like trap them, right, in the vortex core, right, at the tip vertices. That's basically the jet regime. That's how it starts out. Okay, that's the jet regime. So that movement, right, when you see the two tails basically there, the trails, the contrails, right, it's not turbulent there. It's not turbulent there. It's just the exhaust gas is just there. The reason it is all concentrated and moving into lines is because of the induced velocities of the trailing vortices, and they kind of keep them moving because of the induced velocities, and they concentrate them and isolate them in the vortex core. Okay? And then that is essentially the jet regime, and then of course they travel downstream, these vortices, right, and they also sink below the level of the in the primary wake. Okay, that is the vortex regime, and finally, when it comes to the dissipation regime, there it breaks up, okay, and breaks up into the turbulence, and its energy dissipates. Okay, and once it it sort of completes the dissipation regime, the aircraft induced motions, okay, ceases. Okay, it kind of stops. The effect of the aircraft kind of stops, or so to say, the effect of the primary wake or the tip vortices stops, and then the atmospheric processes transport and diffuse the emissions further on. Okay, that kind of gives you a picture of what's actually going on in the contrails, right? So right when it is sort of attached, near the the aircraft body. Okay, so this is something to look at. The concentration, the exhaust concentration distribution. Okay? This is how it looks like, and this is a time variant description of how the concentration kind of looks like, how it's changing. Okay, so look at something like that. Will give more details about the turbulent nature of it. Okay? So similarly, I'm looking at plots from the reference I cited. Right? For example, here this is a the 747 rate. Maximum exhaust temperature, okay, and entrainment rate. Oh my God, that's what I'm looking at. Okay, I'm looking at this plot here. Entrainment rate. So jet is still about 20 seconds. Okay. Jet is about 20 seconds. Okay. Now vortex until 130 seconds. Right. And dispersion is after 130 seconds. And basically the solid or the dashed, the solid lines indicate no atmospheric turbulence. Okay? Solid dashed lines. Then here is the history of the average exhaust. Right, so I think, as if you look at this reference, and between say 1.5 and 3 minutes, okay, they really find that there is no turbulence. So like I said, it's finally at the final dissipation stage, when the effect of the aircraft has ceased, okay, then atmospheric turbulence comes into atmospheric processes, transport and diffuse the emissions further. Okay. So although these contrails are actually not turbulent, although they look like that. Okay?
Also, so this is a development of cyclones actually. Okay. Before I do that, so just think about this. Just now in the previous slide, I was asking that why aren't these nice and plain, and just like a pipe? Why aren't they like that? Just think about it. If I did have fluid flow, which would just be plain and nice and long, would we have something like this? Would we have a cyclone where actually the fluid is going to whirl and turn around, right? It's going to be swirling. So there's a swirling mass of fluid. That's a cyclone, right? So that's what it is. And then it has this snout, and this can be actually so powerful, it can actually lift up complete buildings and trucks and cars, of course. Yeah. Okay, this is very interesting. I put these two pictures together, which is very interesting. The one on the right hand side is actually, the storm in the Indian Ocean, in the Bay of Bengal, which is basically Ayla in 2009, and it's a satellite picture. Okay, and again, something to notice here is this whole white thing going on here, yeah. And then again, I might as well sort of point that out. See, again, you have a little bit of an eye, and there seems to be a lot. This seems to be a lot of swirling of the fluids, right? Would I be right in drawing that? Drawing something like that. Okay, interesting. Now, this is for you to look at. Right? So this is the storm which has developed, and this one, on the other hand, is nothing but your sink, right? So next time, what you should do, if you actually even have a magnifying glass or something at home, right, or even take a 50x zoom in a camera or something. I haven't done that myself. Maybe I should, So just look at your sink. That sink is a great source of information about a lot of things. You have this water which is in a sink. In a kitchen sink, wherever, you just have that, and this is how the flow structure looks like. It looks pretty complex to me, right? You could also do things which, you could just, fill up your sink, like use a stopper here, you fill up your sink, and then just remove the stopper and see what happens, right? Watch it, make a video, watch it over and over again. It'll be fun, try to do that. Okay. All right. So I do interesting kind of work going on with in my group now. So this is something. This is actually we were working on the flow across an airplane wing actually. So we do that, and we were doing an oil flow visualization, trying to see what's going on here, and so essentially, the black part that you see here is where the oil is not there, right? So it's all sort of removed, and so we're actually able to sort of see that, and after that we kind of see that oil, So we think that the flow comes here. This is the flow is actually this way, okay, from top to bottom. So the flow comes in here, pushes the oil. It pushes the oil into along this edge, right, from the leading edge to the trailing edge. So it pushes the oil in this direction, which is actually the chord direction, and then again it sort of leaves it. The flow just is now leaving the surface. It's not doing anything to the oil, and again it sort of touches back and forces it out. So therefore we think that this is a laminar separation. The moment separation happens, it has to be turbulent. So now when I look at these things here, too many vertical structures are in here, too many flow structures are here, some big, some small, some quite distinct, some a little blurred out, some large, some small, some very, very small. This is exactly how, this is not smoke, by the way, and this is something we were seeing in the aero pictures, like aero show pictures. So this is actually, we are using oil over an airplane wing, which we're testing in the wind tunnel. Okay. So essentially what I'm trying to show here is on this slide. So the one on the left hand side, this is how it looks with just the spray. We spray the wing with oil, right? So this is just the wing with the spray. That's all. There's nothing going on here. We haven't tested anything. Next thing you do is you place it in the wind tunnel, and then you test this, right? Then when I test this, this is the kind of structure which is developed. Okay, so this is what is happening, going on like this. Okay, so all right, so I think we have some of these structures here. Okay, okay, all right. So now what we'll do is we'll look at a couple of videos. Okay, and then maybe we'll discuss a few things for a while. Okay, now this is very interesting. Okay, since I showed you. Since I showed you that, might as well. Okay, let me show you this. Okay, this is a slightly sort of a long video, but do look at this. Okay, so do watch this. Okay, I don't have a sound for this. So if you see from the left to the right, you see how the flow develops, right? So initially just had the spray, and now the flow is developing. Let's be a little patient and sort of watch this. Okay, see what's going on with the flow. All right. I can speed this up a little bit maybe. Or maybe not. You just miss out on a few things. You can see how the structures are changing and developing, how new structures are forming. Things that's beginning to happen right now. Yeah. Let me fast forward that a little bit. Okay. So you see this, so this is all developing, right? See how this is being sort of pushed, right? Slightly long video, so you need a little bit of patience to watch this. Okay. Okay, interesting, right? How the complete flow structure is now, a lot of things developed, and now it's all been wiped out and it's all nice and clean. Interesting, right? Okay. Now I'm going to show you something like this here. Now this is actually, I'll tell you what is going on here. Okay. Well, you can watch the video for a bit and then we'll say again. Okay, I'm going to stop this. So you have this is called a bluff body actually. You can see it's not very streamlined, it's a bluff body. And this is at an angle of attack. You can see it's placed at an angle of attack of 4 degrees. Okay, so this is, yeah. And it is facing up to a flow which is at a Mach number around 0.85. Right, which is in the transonic range. That's what we're trying to do here. So what we're seeing here, this black thing, right here, this black on the top and here, this is actually a shock wave. The boundaryless, this is a shock wave, and these things, undulations here, right here, is interacting with this separated boundary layer, and you can see this flow. This is very highly unsteady at instant of time. So this video is made for a certain instant of time. So let us watch this. Right, you see how this tail thing is the tail of that, shock wave is moving, right? It is highly unsteady. And then I'm going to just play that one more time, okay? And then you see the unsteady, this kind of a flow which is going on here. The idea is that how would you define that flow? So that this flow which is happening, right? It's a nice plain flow which comes in and then it encounters this body and see what is going on with the flow, right? Now, how would you describe this flow actually? How would you describe this flow, right? That would be an interesting question to ask, okay? Now, that same body, right? The same body, now I have that with a spike. Okay, this is very interesting. And the same thing, the same body along with, it's in a Mach 0.85 flow, right. So, what you basically see is that we have lost that tail, right, and there's a little more, this is a little more stable. There is a flow, which is like quite unruly, so to speak, which is towards the edge, right, which is towards the end of this whole body, near the neck actually. It's restricted to that, unlike in the previous case. Okay. All right. I think now that we've taken stock of a couple of pictures and some videos, okay, I think it's time for us to sort of go back to our writing board and see what we can do. Okay. All right. So now I think the idea here is now that you've looked at it, okay. So essentially I'm trying to see, what is this turbulence and why is this even important, Is this such an important, phenomena that we have to come and do a class and listen to somebody like for 40 hours, 40 lectures, right? So the point is, what is exciting about it in any ways, right? Is it a bad thing or a good thing, or what is this whole thing? Okay, so let's figure out, let's see if, things make some sense and, we can understand a few things regarding. So essentially, every time you saw some white water, right, every time you saw some unruly sort of behavior in gas, also you saw things in water, right, and you saw things in air, right. So it could happen anywhere, and also you saw that it could, happen in an ocean, in an ocean, and it could also happen in a flow which is as high a speed as nearly Mach 1, right? So it could happen at various, which I showed you in the first slide itself. It could be subsonic, it could be, transonic, supersonic, high alpha. Turbulence is everywhere. Okay, so when you saw all that sort of flow, what did you think? What are the things that you could probably, the moment you see this, how do you describe that flow? So I think that's what I will do right now. Okay, so if I were to sort of just say, my observations about a flow which I see, which is not nice and it's not moving and just by itself still. It's just still. How is this flow different from that, right? So that's what I'm trying to write out. So let's just say, I'm going to just write out, okay, and say the flow is unsteady. We saw an example of that, right? For the flow past the bluff body in the transonic flow. Unsteady. And also the flow over the wing, right? When we're doing all flow visualizing, that's also very, very unsteady, right? Irregular. Random, I didn't find anything particularly orderly about this. It was pretty random, Well, chaos is actually a physical phenomena. I use the word chaotic basically, as an English word here. Okay. So flow is unsteady, it is irregular, it is random, it is chaotic. motions of many length scales are observed. Would you say that, right? If you look at the videos again, motions of many length scales, like I showed you, even for the air shows, somewhere it is, quite, close together, it's closely packed. Now slowly it's sort of spread out a little bit, and then for the flow over the wing surface, right? It was quite interesting because slowly the flow structures developed. Sometimes some was a little long, some a little round, some were of different sizes, of course, right? So, and motions were happening for all of them. So motions of many length scales, motions of many length scales are observed. Okay. Okay, so this is something that we've observed, right? So to bring in the small things that I'm pointing out here, so essentially we are talking about, say, this is what it looks like, right? So now, should I tell you that this is what is turbulence? I tell you and you believe me? Not really, but since people have been studying turbulence for quite some time, so there are some basic understanding of that. So I'm trying to jot that down first, okay? But we will observe this on our own and for ourselves individually as we go along, and then we'll sort of see whether all of these observations make sense. Okay, so as of now, I'm basically kind of writing down or jotting down the observations made in terms of what a turbulent flow will be like, right, with years of research. Okay. Now, fluid velocity varies significantly. And irregularly with space and time. That is right. Now, it will be interesting if you go back to the Hawaii picture, right? And there were so many different blues, right? And even in the big ocean, there are a few places which is like really calm, and then some places there was white water. Places the color difference is of course for a different reason, but definitely the flow itself, the wave, the size of the wave itself is different at different places, right? So therefore, the movement of the fluid, which is fluid velocity, is different. It's varying quite significantly as we move in space and as we look at the same picture over instances of time, right? And there's no pattern to that, of course, so therefore it is irregular, right? So and therefore studying how the ocean surface behave is a very significant job for oceanographers, people from ocean engineering actually. So it's a very important study to do. So it's very difficult to say the height of the surface of how the surface will behave. It's very difficult to sort of draw a nice surface on the ocean. Okay. So all of these behaviors, the point is all of these, if the flow is unsteady, irregular, random, chaotic, if the motions of several length scales are present, in the flow. So given, a certain domain of flow, there are motions which are happening on a large mass of the fluid, slightly medium mass of the fluid, slightly very small mass of the fluid, which basically motions of many length scales are observed, right? And again, the fluid, the velocity, the fluid is moving very, very, distinctly, and there is a very stark difference between the velocities of the fluid in one place to the other, and there is of course no regularity or regular pattern to the change. So everything is irregular, and that's happening over time and also as we move along into the domain, right? So all of this is basically telling me that the flow is turbulent, right? So therefore this also means that if you have to study turbulence, that means these are all the properties of the fluid that will come into the picture. You see the number of variables that there are, unsteady, then irregular, then random, then chaotic. How do we quantify all of these things, to finally say that I know what my turbulent flow looks like, or can we even do that, right? So we'll do the best we can, let's put it that way, okay? So we're not sort of taking on nature, can we? Okay. Ability to transport and mix fluid more effectively. That is very interesting, right? Ability to transport and mix fluid more effectively than a comparable laminar flow. Not sure what the word comparable laminar flow would be. When I say, I guess, because the Reynolds numbers are going to be different. Comparable meaning in the, I guess, in the length scale, in the same length scale. Okay. Now, this is a very interesting thing. Now, just think about it. Now, if when you add sugar to your tea, you shouldn't, but you do. So when you do that, how do you mix it? If somebody says mix it, what is the best way to mix it? Think about this. When you mix, I don't know if you've seen this, but if there's really, really hot milk, right, and you want to sort of, bring it to the room temperature so that you can drink it, right, then you take that glass of milk or in the bottle of milk and you pour it, in a quite distance, and you do that. You keep pouring between the two, vessels, two glasses maybe. You keep doing that, right? So you do that, and when you pour the milk, you should see how that milk, have you seen? It kind of, it's almost like a pipe and it reaches the other one. Have you seen doing that, right? Interesting. So when you do that, and it does cool down, it does cool down pretty effectively, try this. So you do that, right? And or just keep that glass of water, a glass of milk under a fan or something, or just leave it. Just leave it at room temperature. Eventually, it will cool down. Eventually, anyway, it will cool down. But then, why, number one, do we switch on the fan? Maybe. And why do we do this? This seems to be very effective. You take it between two glasses, and then you do that. Why do you do that? Right? Interesting. And when you do that, you see how that same milk behaves. Right? Does the milk flow structure, is that different? Okay, it is to look at. So now, like I said, you take in your tea, you put some sugar, and what do? Right? You take a spoon and you stir it. You mix it. Say you mix it, right? So, so when you have, so basically you take it, right? You take and you just move it randomly, just stir it like that, right? So therefore, some random, or chaotic or irregular movements is useful, right, if I want to mix something, right. So, a turbulent flow should be good in that, right, turbulent flow should be good in that, and that is why I said just think about it. So, therefore, when the smoke comes out, what is going on there? Smoke is it will have particles, right. So, you have smoke, right, and then you place it near a heat source, which is the candle. See how that will behave, right. It will be very interesting. Okay, so ability to transport and mix fluid more effectively than a comparable laminar flow, that is your turbulent flow. Okay. Now, there are some this is something which is so Osborne-Reynolds experiment. Okay. Maybe you can sort of remind yourself what this is, or if you are not aware, just look at a basic textbook and you should be able to get that. Okay. So, the back in 1883. So, Osborne-Reynolds experiment is essentially characterized by Reynolds number. By Reynolds number, right. So, essentially you have a pipe, okay, there's a fluid flow, right, which is happening. There's a fluid flow which is happening, right, and then we inject dye, right, along the center line, right, and this is a pipe. Now, for this particular experiment, so he basically, the Reynolds experiment, he basically came up with certain values. We basically said that Reynolds number is less than 2300, means the flow is laminar. Reynolds number is larger than about 4000, it is, right. So, whether the flow is laminar or turbulent definitely depends on the speed. So, it is essentially dependent on more things than just speed. So, therefore, it is essentially it is characterized by the Reynolds number, and these are some values that Osborne-Reynolds came up with, in the 19th century actually. Okay. All right. So, now again, okay, let's go to that one. Okay. So, a turbulent flow, yeah, well, like I said, the turbulent flow consists of different motions at different length scales. I think we've spoken about that, right. So, okay, let me still write this. So, turbulent flow consists of motions in different length scales. Okay. So, well, this is trivial, I guess. This is small scale turbulence and large scale turbulence, I guess. Okay. Now, so this I think we just said that, you know, we've been seeing that also in you know, all the turbulent flow that is around us, you know. And I think it's high time now that you start looking around and see, you know, essentially everything is right here in nature. It's around us, you know. So we don't need to really lock ourselves in a room and, you know, look at a black thing and then only learn things. You basically learn from everywhere, you know. You just notice things, right? You see a little, when it rains, you see a little muddy puddle, right? And you see how the water behaves. And you see a little bit of stream that has formed, you know, just a foot long. And you see how the water is, you know, skipping over small little rocks, you know. You see little white waters there as well. In such small scales also you'll have turbulence, right? So obviously the turbulence that you're having in, like in a muddy puddle and in a rain, you know, in a small little drain right outside your, you know, house maybe, and then you also have turbulent flows in a big ocean, in a small part of it, on a big part of it, in a large scale part of it. So when you have large, you know, waves, you know, you have white water there, and then when you saw the water is essentially calm, but in a little place you have a little white thing going on, right? So turbulence does consist of several motions in very different large, you know, length scales. So the small scale and the large scale, right? So the small scales now. So now next question is then, what makes it large and what makes it small? So now we're getting into the groove, right? Okay. So small scale motions depend on the rate at which they receive energy from large scale motions and viscosity. These are independent of flow geometry. Okay, so I'm going to see right now, I'm going to just write these down, and slowly as we move in, you will see that, you know, things will explain themselves, I guess, okay, as we discuss. So small scale motions depend on the rate at which they receive energy from the large scale motions, right? Motions, they depend on viscosity, they are independent of geometry. So I'm not going to dwell on this too much, because we're going to study this in detail, right? This is called something called an energy cascade. So when we get there, we're going to study this, okay? But by this time you must have thought that, you know, if there is so many motions, right, the energy has to come from somewhere. You know, where is this energy suddenly coming? You know, where is it getting this from? Because, like I said, you know, you have a nice still water. You have a nice still water in a pond, but then in a lake. But then suddenly you go to an ocean and then you see all sorts of movement, right? Where is this coming from? It's getting its energy from somewhere, right? So why is it that some are big and some are small, right? Or is the one which is big at a instant of time given a location, is it going to remain like that? No, like we said, it's all very unsteady and irregular and chaotic. So that's going to change. If it's going to change, it's going to change its size, sure, right? So then what will happen to the energy? Now that it's smaller, right, it needs less energy. What happens to that, that extra energy, right? So it can't be destroyed, so it will be transferred to somebody, right? So therefore, and maybe that energy is small enough, so then there will be a motion which is on a small scale. So that is what I guess at this point, the way to understand what I've just written is that the small scale motion depends, at which rate they receive energy from the large scale, right? And of course the viscosity, and it is independent of the geometry, right? It doesn't depend on the geometry. Okay. So, large scale motions are strongly influenced by the geometry. So, large scale motions are strongly influenced by the geometry, right? And they also control transport and mixing. They also control transport and mixing. Okay. So good. I think we will. So that's about to say. I will. I think nothing more to explain here. So we will sort of do it in the next class. I think what we start doing next class is looking at, now that we've sort of got some idea of how turbulence, what turbulence is, and we have looked at pictures, etc., how turbulence is all around us, etc., etc. Let's look at some of the very basic equations, right? So essentially, I'm not talking about it's not like a density, So how will you define this turbulence then? So when I said that we have the flow is unsteady, irregular, random, chaotic, what is? So quantify it. What exactly in the flow is unsteady, irregular, random and chaotic? I mean, this is something nice to talk about, but then if I had to write a computer code, trying to understand a turbulent flow, what will I tell it? What will I tell how will I direct the computer code to solve my problem, right? So then we will need some kind of variables. What are those variables? What is it that is unsteady, irregular, random and chaotic? Motions of many length scales, if this is happening, then density is changing, viscosity is changing. What is going on in turbulence, right? So those are the type of things we will get into slowly, right? And what is going on with the so I think we'll start looking at equations, and this is still sort of introducing the whole concept of turbulence. So that's where we are going to go into, right? So we're still trying to really understand what this sort of emotion is all about. So all of this, let me just sort of say that. So all of these things that these properties, essentially what we're talking about here, all of this is essentially nothing but turbulent flow. These properties, right? And the next one also. Here, of course, I have written it, the turbulent flow is so and so. So these are essentially the basic, gist of how turbulent flow behaves and consists of, right? How it looks like. And we've seen some pictures and seen some of that. So I'll stop here and take it up again in the next one. Okay. Thank you very much.